All right, y'all. True titrations. We're looking at the problem that says 25 milliliter sample of 0.1 molar lactic acid is being added. We're going to look at this full titration. So let's dive in and check it out. Okay, so it wants the starting pH of the sample because A says 0.0 milliliters. All right, so the sample that we're looking at, the lactic acid, is a weak sample. All right, I know it's weak because of the carbon in this acid. All right, so I'm going to add it to water in a rice table because that's how we find the pH of a weak sample. All right, so let's get this problem going. So my Bronsted-Lowry here is going to have the acid donate because that's what it wants to do. All right, so I just moved an H over there. I is for initial concentration. So if you go back to the problem, you can see that my concentration is 0.1 molar of that sample of the weak. So there's the 0.1. And there won't be any of those things initially in my, my A part of this problem. So we will track the change. All right, I'm given a Ka of, I keep losing the problem, 1.4 E negative 4. Now, I don't have to convert this Ka because look, the X that I'm solving for is connected to hydronium. So this is nice. It's not hydrolysis, which is why it's not automatically wrong. This is just the pH of a weak sample. So I can just use this Ka value in my products over reactant problem. To solve for X. So we will cross multiply into a 0 equals equation. And we'll come up with 0 equals the X squared we never mess with. All right, and then we cross multiply but switch the signs to get it away from the 0. So times the negative X is going to be a positive expression. And then distribute towards the positive and it will become a negative function. And I get 1.4 E negative, oh yeah. In your solver, you'll find that X has a value of 3.81 E negative 3. This X value is defining that X, which is the hydronium. Catherine, you can still ask questions even though we're recording.
Okay. So for the FRQ, you know, for like the first question, part C. Yeah. Okay. So yesterday you told us to use the 0.0374 like moles, I think.
Right. Does this have to do with this question that I'm working on? Are you connecting the two?
No, I think they're totally different.
No, wait, you asked me to do this though, right?
Yes, I did ask you. But like, I could ask questions like how to.
Yeah, no. Questions about this. I need to finish this problem. because you asked me to work this problem out.
Okay.
Wait, I'm so confused now. Didn't you ask me to do this problem?
Yes.
Okay. All right. All I meant was if you have questions about what I'm doing here, you can stop me. Don't ask a new question. Let me finish this. So we're trying to find out the pH. So if I just take the negative log, all right, it is going to give me the pH because it's already of the H3O plus, and I get 2.42. All right, so this is part A before any of the titration happened. And now part B wants us to start doing the titration. So that's your pH there. But the titration is going to start mixing the strong sample, which it says that we're adding sodium hydroxide. So I'm just going to focus on the hydroxide because that's what makes him strong. And it's being titrated into the analyte of the lactic acid. All right, I'm just going to write it like that. All right, I'm cheating, lactic acid, but you know that it's there. Anyway, we know that we want to donate an H to the base, which is going to form water. All right, and then we'll just have the lactate ion over there. And now we can start our normal titration. So if we go back to the problem and look, remember the amount of moles of the analyte is never going to change. So it appears that we need to multiply 0.1 molar. All right, we need to go 0.1 molar times 25 milliliters. All right, and that'll give me the moles of the lactic acid to be 0.0025. And that's the number that will never change. Okay. Now the hydroxide on this titration, it says that we're adding 4 mils. All right, so if I do the same thing where I multiply the 4 mils by the given molarity of the strong, which is 0.1, we're going to get 4E negative 4 here for those moles. It's just an easier way to write it instead of writing a bunch of zeros, right? So I want to compare which of these two values is smaller. It's this one. So we'll subtract this amount from both. Of course, we want to shift up over here. So the strong sample has lost, and I need to find these two amounts, which will come out to 0.00210 there. And then this will just be 4E negative 4. And now here's where I can see that I have a buffer, right? Because I've got both components of a buffered system. So we can cheat and use these mole counts in the Henderson equation instead of going to molarity. So it'll say that pH is going to be equal to the pKa. All right, that Ka is given at the 1.4 E negative 4. Plus the log of the ion over the weak. So this will be the 4.00 E negative 4 over 0.00210. and I get a pH of 3.13. And of course, those of y'all watching the video, you can be pausing to verify these numbers as I kind of just work through the steps with you. All right, now part C, part C simply changes the amount of the strong that's added. So a lot of this stuff stays the same. But for this step in the hydroxide, I'm instead going to be multiplying, again, the strength of the hydroxide was 0.1, so it'll be 0.1 molar, but now I'm adding 12.5 mils. All right, so there's the 12.5 mils written as liters, and my mole count now is going to be 0.00125. All right, so now we just have to analyze the titration from this standpoint by, again, subtracting. The strong loses. Shift up. All right, and look, they're the same number now, which means we could just take the negative log of this and we'll get the same answer, but that's the way that it would look if you had all the info in there. And I get a pH here of 3.85. All right, then it talks about the equivalence point.
Yes, in part D.
All right, so let's look at that.
Are we gonna like use a KB?
Well, we know that by definition, the equivalence point is going to be when these two guys are the exact same, right? So they both zero out. And it's going to make this dude over here shift up by that much. All right, but this question wants to know, well, first we need to figure out the liters, right, to get to the equivalence point. Maybe. So this is the number of moles I need to get to, but I know that the OH minus is existing at 0.1 molar. All right, and since molarity is moles over liters, all right, to find the volume required to reach the equivalence point, which isn't necessarily what the question's asking for, but I need to know that liters in order to get these moles back into molarity. I need to know how much volume has been added. All right, so I'm just going to plug and chug. The molarity is 0.1. All right, I want the moles to be 0.00250. All right, so I can solve for liters there. All right, and we are going to get 0.025. All right, so there's the amount of the titrant needed to get to the equivalence point. But then look, just like we've done in 2 other problems in this tutoring session, like all of you video people at home can find in a million hydrolysis questions. In order to find the pH, we don't have the strong winning. We don't have a buffered system because we are missing part of the buffer. All we have is this amount of the offspring of salt. So I would do another hydrolysis problem, all right? Add him to water in a rice table, all right? We don't want moles, we want molarity, so we would divide it by the sum of the 2 volumes that have been mixed together. And we would go through hydrolysis, all right? So you could get that answer by doing that, but school's about to start, so I have to finish right here. But let's do E really quick. All right, look at E where we go 5 mils past the equivalence point. All right, so again, a lot of this stays the same. We're gonna go 5 mils past the equivalence point. So if I do that, that's gonna put me at $30 mils. Ugh. Sorry, looked like my work was wrong. All right, so we're dealing with 30 milliliters here. All right, so here we go. 30 milliliters times hydroxide's 0.1 molarity is going to give me a count of 0.003. All right, so now the strong has won, so I will subtract this number here, and I'm going to get 0.00050 moles. And we know that whenever the strong wins, we only care about the strong, right? Because this would shift up over here for the lactate, but who cares? Because the strong won. So I'm going to go ahead and divide these moles by liters. All right, now be careful because we added 25 and then we added 5, which was the 30. All right, but that is being added to a 25. All right, initially there was 25 mils in there. We're saying that we have added 30 mils through titration. Whoops. Therefore, the total mils is going to be 55 milliliters. So I'm going to divide this then by 0.0055. All right, because that's how many, that's where we're at there. Oh, that's too many zeros. I was going to say, not 5.5 mils. Can you tell the bell's about to ring on me? All right, 55 milliliters. All right, and when we do that, it's going to give me a molarity of 0.00909. What's that? Yeah. I like it when there's someone to give me a thumbs up in the room. Makes me feel good about myself. This molarity is describing this base. And we want pH. So if we take the negative log of that strong basic sample, it'll give me a pOH of 2.041. Therefore, I know I can get to a pH of 11.96. Or maybe 960. Look back over my work is messy on this problem. Catherine, the bell is ringing literally right now, but best of luck to you today.
Thank you, Mr. Cummins.